Mechanics of Materials, Chapter 5, Torsions in Non-Circular Members. So in this example, we want to consider the effect of torsion in three non-circular cross-sections, like a cross-section of a square, rectangle, and thin-walled rectangle, a square. So in our problem, if we are applying a allowable tau, like tau allowable, acceptable or allowable shear stress is 40 megapascal, we want to determine the largest torque which is applied to each of these brass bars cross sections. So cross section 1 is like a 40 times 40 square cross section column, brass column. The second one is 25 times 64 millimeters rectangular section, and the last one, the third one, is 40 times 40, but with a thickness of 6 millimeters, which is a thin-walled hollowed section. So let's see how we can approach this problem to calculate the torque required for each of them to work with this acceptable shear stress, to create this acceptable shear stress. What is the maximum torsion? So like T sub 1, T sub 2, and T sub 3. Let's jump to the problem. So the very first case is like a non-circular section, as you can see here. And the formula for a non-circular cross-section is tau maximum is equal to maximum torsion, or T over C sub 1 A B squared. So if you look at our cross-section, A and B are equal to each other. So if you have a tau maximum equal to tau allowable, which is given or provided in problem statement, A is equal to B, and both of them are 40 millimeters or 0.04 meters, and the ratio is 1. As soon as you know the ratio of A over B, we can just jump to the table and read the C sub 1 value, replace in the equation, and get the only unknown of problem, which is T1. So T1 is easily calculated to be 532 Newton meters for the very first case. And then if we want to see the effect of rectangular cross section, what is the maximum torsion, or T sub 2 in the second case? Again, it's a non-circular section. We need the ratio of A over B, and that's A is 64 millimeters, thickness is a 25, and if you divide that, it just gives us 2.56. And if you jump to the table of A over B ratio, you can interpolate between 2.5 and 3 to get the desired value for your C sub 1. And if you do so, it's something between these two numbers. And by interpolation, you get the exact numeric value of 0.259. And if you again plug it back to the main equation over here, it just gives you the numeric value of T sub 2 is equal to 414 Newton meters. And let's move to the last case, which is a thin-walled hollow section. So this is a narrow strip of all the way round, and the other part is hollowed part. So for the hollow thin-walled cube sections, tau shear stress is equal to this equation, T over 2 times A average times the thickness. And A average is nothing but just 40 minus 6 millimeters, 40 minus 6 millimeters from each side. So that make it 40 minus 6 squared times 10 to negative 6 conversion to meter from millimeters. And it just gives us a numeric value of 1.156 times 10 to negative 3 meter squared. And if you plug that back into main equation like here, it just gives us a T3 is equal to 555 Newton meters. And that's all what we need to calculate for this problem. And if we want to make a comparison between the first case and the last case, because their dimensions both are equal, identical to each other, except the last one is a hollow thin cross section. Comparing the capacity of the bar of solid square, the solid one with that the tube one, the same dimension, but the hollowed one demonstrate the ability of the tube to carry larger torque. So if you come back to the numeric value we calculated, you can easily see the paragraph says that the torsional torque which the hollowed section receive is higher than the solid square section. And that's interesting. And the logic of that is, if you look at the nature of these two equations, for non-circular solid one, tau maximum is T over C sub 1 AB squared, and for this one is shear is T over 2 times average area times the thickness. And if you just move into the numeric value and plug it in the denominator of both of equations, you can easily see, one can easily say 40 squared is almost equal to 34 squared, but most of the time one can say that multiplication of c sub 1 times the dimension is far less than the thickness of the plate, and that's why we get a higher torsion in the hollowed section all the time in comparison to the solid squares. Thank you. We'll solve more problems.